Hey guys, so today's video is going to be on some conceptual principles for momentum. So to get started, I'm just going to write out what we all probably already should know at least, is that momentum equals mass times velocity, right? So momentum equals mass times velocity. And before we get started, I'm going to show you guys how this came about or why it exists. And the first step is to use Newton's second law, right? We all should be familiar with this by now. It's force equals mass times acceleration. And if I look into the acceleration, we know that the acceleration is the derivative of velocity, so that equals change in velocity over time. So I'm going to have my force equals mass. Change in velocity could be written as velocity final minus velocity initial over change in time. Right? And hopefully this is starting to look familiar. It looks like mv final minus mv initial over change in time. And from up top we already know that mv is our momentum, so force is going to equal change in momentum over change in time, which equals mass times acceleration. I think that's really neat, and actually I found out that Newton made his first second law relationship in respect to momentum, not mass times acceleration. So that's kind of neat, and that's how momentum comes about. But the actual usefulness of momentum comes through the fact that it can be used to analyze elastic and inelastic collisions. So I'm going to write those right here: inelastic and elastic. Okay, so I'm going to start with the easy one, which is inelastic, so i.e. inelastic. Now in inelastic collisions, basically what happens is, I think this is the stereotypical example, you're going to have some ball, so you're going to have ball 1 and ball 2, right? And before anything happens, you're going to have ball 1 moving at ball 2, and ball 2 is stationary, right? It doesn't have to be stationary, but the equation I'm about to show you works only if ball 2 is stationary. So ball 1's moving towards ball 2 is stationary, and that's the before, and afterward you're going to have ball 1, and ball 2 is just kind of fused into ball 1, so they're kind of together now, and they're both moving at some velocity, right? So some random velocity. Okay, so using momentum, what we can do is we can say that the mass of the first ball times the velocity initial of the first ball plus the mass of the second ball times the velocity initial of the second ball, which this side of the equation for inelastic should normally be 0 because you're going to look at 2, which is stationary, is going to equal your m final. So your m final is going to be the mass of both of them added up, so m1 plus m2 multiplied by the v final of both balls, right? Because they're combined. Remember, in inelastic they're going to be combined. Think about it like clay balls or something. So that's the easy way, and from that you should be able to get most of your calculations. But now the hard way is elastic collisions, which is, so if we look at the same model, ball 1, ball 2, but in the after, so ball 1's moving, in the after, ball 1 is going to go maybe to the left and ball 2 is going to go to the right, right? So think about something like bouncy balls. They're going to bounce off each other. And so the equation which physicists have already derived for us is this one. So if you want your velocity final for ball 1, right? And we have to remember, once again, I'm going to put a star right here because this only works if ball 2 is stationary to begin with. So velocity final 1 is going to equal your m1 minus m2 over m1 plus m2 multiplied by velocity initial of 1, right? And this kind of makes sense because your ball 1 or velocity of 1 is the only thing which should influence your final velocity, right? Because the ball 2 is stationary. And your velocity final of 2 equals 2m1 over m1 plus m2 times velocity initial of 1, right? So these are some good to know equations. I mean, I'm sure on a test you could derive for them, but this would save you a ton of time. And finally, what I want to end with is something called the impulse momentum theorem. So the impulse momentum theorem states that your change in momentum, or delta p, equals impulse, which is represented by capital J subscript x, right? And this, so the easiest way to show this is if I have a graph, right? On my x-axis I'm going to have time, and on my y it's going to be force. It's going to look something like that, right? Basically what this states is that the area underneath this force with respect to time curve, it equals my impulse. That's what an impulse is. So an impulse is what, if you throw a bouncy ball at the wall, it's going to bounce back. The change in momentum is caused by the impulse. And that's why a bouncy ball has a larger change in momentum than a clay ball, which would just stick to the wall and not bounce back. Right? So a calculus way to write this is that your impulse is going to equal your integral from time initial to time final of your force with respect to time. Right? And I'm running out of time, but I'm going to make a real quick connection to work, which occurs later on in, I think, chapter 11. But your work, if you remember, your work is actually your integral from x naught to x final, so distance initial to distance final of your force with respect to distance curve, right? So there's a pretty big similarity between the two, and I think that's something worth taking note of. Right, so in a graph, if I draw a graph, you're now basically in your x-axis you're going to have some measure of distance and you're going to have force, but you could have this thing looking like the same, and the area underneath the curve is going to be work, right? So capital W. That's where I'm going to end this video because I'm already touching at 7 minutes, but hopefully this helped you guys, and I think I'm going to be making a second one on energy and how that relates to momentum. So hopefully this helped, and good luck on the test.